3.6, factoring polynomials. Okay, so we're going to touch on the factor theorem now. So as we call f at x, so our expanded version of our function is the quotient times the divisor plus the remainder. Okay, and as a recall, if the remainder equals 0, we know that a polynomial f at x can be broken down into two factors. Those two factors are going to be q at x and d at x, right? Our quotient and our divisor. Using what we know from remainder theorem, we can understand that factor theorem, here we go, f at k equals 0 if and only if x minus k is a factor of f at x. Okay, so verify that x plus 3 and x minus 2 are factors of this function f at x. So we can go ahead and find the root. So the root for x plus 3 is, let's go x equals negative 3. Give more room. And the root for x minus 2 is x equals 2. So using remainder theorem, we can go ahead and sub in f at 2 and then f at 3. So 3 times 2 cubed plus 2 times 2 squared minus 19 times 2 plus 6. And then 3 times 3 cubed plus 2 times 3 squared minus 19 times 3 plus 6. And we can go ahead and we can plug those into our calculators. So this one, and I'm doing this across the page just to save a little bit of space. We would get 24 plus 8 minus 38 plus 6 which is 0. Okay, and then this one we would get 81 plus 18 minus 57 plus 6. And if we put that into our calculators, sorry, this is negative 3. I'm going to put green, negative 3, negative 3. So this one's going to be negative 81 plus 18. This is going to be plus 57 plus 6. And there we go. Now it's 0. So factoring polynomials fully. There are two ways to try factoring a polynomial of 4 or more terms. Okay, number 1, we have grouping. And number 2, we can use the factor theorem and division of polynomials. Okay, so for example 2, let's try factor by grouping. So we have 4 terms. We're going to group the first 2, group the second 2. And then what you want to do is you want to common factor 3 times. So let's take out an x cubed out of the first 2 terms. X cubed is our common factor, and we're left with x minus 6. Then out of the second 2 terms, we're going to factor out a 2x. So positive 2x is our factor, and x minus 6 is what's left over. Okay. Now we have 2 terms, because remember, terms are separated by plus or minus signs, which we have here. And we can factor out an x minus 6, because x minus 6 is identical in both terms. So this time our common factor is x minus 6, and we have x cubed left over, and then 2x left over. Right? I didn't notice this in the first step, but if you can see x cubed plus 2x, we can actually factor out an x out of there. So let's go ahead and factor out an x. We'll have x minus 6, right? We're just bringing that down. And then what we're left with here is x squared plus 2. And the reason why I noticed that now is because I was looking at this and I was wondering if it was fully factored. So now it's fully factored. Okay, x can't be factored anymore, x minus 6 can't be factored anymore, and x squared plus 2 cannot be factored anymore. So if you cannot factor by grouping, you will need to gradually break a polynomial down by dividing out its factors with long division, okay, or synthetic division. So for the rest of this course, I'm going to be using synthetic division. If you choose to use long division, that's totally fine. It may be a little bit time consuming, but that's okay. All you need to know is the value of one of the polynomial zeros to begin. Okay, so this is where our next theorem comes in. If f is a polynomial with degree n is greater than 1, then it is possible to make an organized list of potential rational numbers. Okay, rational is a over b, it's a fraction. Okay, to aid in finding the zeros of the function using the rational zeros theorem. Okay, so that's what we're going to be touching on right now. Rational zeros theorem. So if f at x is a polynomial with integer coefficients, and if ax minus b is a factor of the polynomial f at x, then b is a factor of the constant term of f at x, and a is a factor of the leading coefficient. So constant and leading coefficient. Okay, factors of these. I'm going to show you guys how we use this. So possible rational zeros. What we want to do is we want to talk about the factors of the constant term and then the factors of the leading coefficient. And then what we're doing is we will put them over each other as a over b. Okay, so example 3, fully factor each of the following polynomials and state the zeros. So the leading coefficient here is 1. Possible factors are just plus minus 1, that's it. So pretty much when the leading coefficient's 1, we kind of just ignore it. Okay, and I'll go over that. The constant term, so I should say a equals, the constant term is 24. Now, the factors of 24 are plus minus 1, 2, 3, 4, 6, 4 times 6, 3 times 8, 2 times 12, and 1 times 24. Okay, if the a value had more factors other than 1, or any other factor other than 1, what we would do is we'd say, see like the possible rational zeros. So what we want to do is we want to list possible factors. I just put PF. And then we make a list. And we are going to put the constant term factors over the leading coefficient factors. Every single one. So we'd have to go 1 over 1, negative 1 over 1, 2 over 1, negative 2 over 1, and so on. Because the denominator would be 1, I'm going to completely ignore that for now. Okay, so possible factors, it's just going to be a replica of this. Plus minus 1, 2, 3, 4, 6, 8, 12, 24. Those are possible factors. Okay, now what we want to do is we want to use the remainder theorem and the factor theorem to determine which one of these is a factor of our equation. So what we have to do is we have to kind of do a trial and error. We have to say, okay, so what is f at 1? And then we literally have to sub in 1. 1 cubed minus 1 squared minus 14 times 1 plus 24. Well, does that give us 0? Is that one a factor? No, it gives us 10. So 1 is not a factor. Okay, we can try negative 1. So negative 1 cubed minus negative 1 squared minus 14 negative 1 plus 24. Putting that into our calculator, so negative 1 minus 1 plus 14 plus 24, I get, I think, 36. Does that equal 0? No, so that's not a factor. And you keep going. So f at 2. 2 cubed minus 2 squared minus 14 times 2 plus 24. Oh, I get 0. So at this point, I know that 2 is a factor. Okay, sorry, 2 is a root. So since 2 is a root, x minus 2 is a factor. Let me scroll down. Okay, so if we know that x minus 2 is a factor, what we can do is we can do synthetic division. Move this up just to save a little bit of space. So our root is 2, and our coefficients are 1, negative 14, 24. Bring down the 1. 2 times 1 is 2. Add these together. 2 plus negative 1 is 1. 2 times 1 is 2. 2 plus negative 14 is negative 12. 2 times 12 is negative 24. Remainder 0. If this remainder is not 0, then you've done something wrong. Okay? Now, what we have right now is x squared plus x minus 12 equals 0. At this point, we can resort back to grade 10 factoring, and we can say what two numbers multiply to negative 12 and add to 1. Okay, I get 4 and 3. The negative is going to be on the 3. So I get x plus 4, x minus 3. Okay, at this point, because we don't need to use the factor theorem again, you don't have to list the possible factors. If we're able to just directly factor it using like product sum, decomposition, difference of squares, and tomorrow difference of cubes, sum of cubes, okay, those techniques, then we no longer have to rewrite the possible factors because we're not using them, we're not checking them. So going back to the original question, fully factor each of the polynomials and state the zeros. Okay, so I'm going to say, let's call this f at x. Okay, I'm going to say that the fully factored version is x minus 2, and that we got from factor theorem, and then x plus 4, x minus 3. And now we can say the zeros are x equals 2, negative 4, and 3. Okay. While we have this up, I'm going to read this. So how to find the zeros. So first, what you want to kind of do is you want to check the degree of the polynomial. In this case, we have degree 3. Therefore, the maximum number of zeros that we have is also 3. Okay? And you want to find all the possible zeros using that rational zero theorem. That's what we did here, possible factors. And then use the remainder theorem to find which number is actually a 0. So again, remainder theorem, we did, and this is completely trial and error. There's a little bit of logic behind it, but it's not concrete. There's only really logic to rule out a couple numbers. Other than that, it's trial and error. So this time we're going to fully factor 3x cubed plus 2x squared minus 7x plus 2. Okay, so the leading coefficient, which is our a value, is 3. Possible factors of 3 are 1 or plus minus 1 plus minus 3. Right? 3 is a prime number, so we only have 2 factors, 1 and 3. Now our constant is 2. So the possible factors of 2 are plus minus 1 and plus minus 2. So now let's list our actual possible factors of this entire equation. So what we want to do is we want to do factors of the constant term divided by factors of the leading coefficient. So let's start with 1. So we're going to have 1 over 1, which is just 1. And by the way, we plus minus everything. Okay, everything could be positive and negative. Okay, and then 1 over 3. Yeah. Now we're on to the 2. Okay, because so constant possible factors over leading coefficient possible factors. So 2 over 1 would just be plus minus 2. And then 2 over 3 would be 2 over 3. And sometimes there's going to be situations where we're like repeating some, and then you can leave those out. So let's go ahead and sub in 1. So when I sub in 1, if you look at what's actually going on, we're just subtracting, like adding and subtracting the coefficients. So when you sub in 1, I'm thinking, okay, 3 plus 2 is 5, minus 7 is negative 2, and then plus 2 is 2. So you can quickly skim, like that's kind of a short form way, you can quickly skim the coefficients and see if it is 1. Okay, and in this case, it is. So our root is 1, and our factor is x minus 1. So let's go ahead and let's put this in synthetic division. Okay, so 3 down, 1 times 3 is 3. Add these together, we get 5. 1 times 5 is 5. Add these together, we get negative 2. 1 times negative 2 is negative 2. Add these together, we get 0. So that's good because it is a factor. 0 remainder. So from here, we have 3x squared plus 5x minus 2. Okay, so let's just bring that up here. So when we have a trinomial, we can see if we can factor this by doing decomposition. So what multiplies to negative 6 and adds to 5? Okay, well the factors of 6 are only 1, 6, 2, and 3. This is a tricky one because 6 minus 1 could give us 5 and 2 plus 3 could give us 5. So we really have to pay attention to the negative signs. So negative 6. What multiplies to negative 6? We have to have at least one negative sign in here. I'm going to say 6 times negative 1 gives us negative 6. 6 minus 1 gives us 5. These two are the factors. So, but they're not the actual factors. These two will allow us to do decomposition. So we take this 5x term. We rewrite the first and the last terms. And then we're going to break down this 5x into negative x plus 6x. That's where these two come into play. And now, just like above, we are going to common factor 3 times. So let's group 2 terms, group the last 2 terms, and see what we can factor out. Okay, so what can we factor out of 3x squared and x? Well, just an x. So put the greatest common factor in front, and we're left with 3x minus 1. Now, what can we factor out of 6x minus 2? Well, 2. So the greatest common factor is positive 2, and we are left with 3x minus 1. And then this is perfect because when we take a look at our 2 terms here, what's identical? Well, the 3x minus 1 is identical. So common factor is 3x minus 1. Then we have x plus 2 left over. Okay, so therefore factored form is 3x minus 1, x plus 2, and don't forget here, x minus 1. Okay, and then the roots from these are going to be 1 over 3, negative 2, and positive 1.